deep dive a little bit to understand how data is actually stored in the computer. Bit is the smallest storage possible in computers. A bit is like a light bulb. It can either be turned on or turned off. A bit can be either a 0 or a 1. If we take 8 bits together, the combination of 8 bits is called a byte. A byte gives us some more options of turning up to 8 bits on or off. Byte is the smallest storage that is meaningful for us for storing numbers and strings, and you will soon see. If we take 1 byte with all 8 bits turned off, we define that to represent the number 0. If we turn on only 1 bit on, the rightmost bit, we define that to represent the number 1. If we turn on just the second bit from the right, we define that byte to represent the number 2. Are you thinking about the number 3? Do you have any guess? Well, we already know how we define 0, 1, and 2 to be represented by byte. Let's see how this has been defined, actually. We assign each bit a number. The rightmost bit is assigned the number 1. The second bit from the right is assigned the number 2. The third bit is assigned the number 4, and so on and so forth. You can see there is a pattern here. 1 multiplied by 2 is 2, 2 multiplied by 2 is 4, 4 multiplied by 2 is 8, etc., etc. Actually, since each bit has only 2 options, this pattern is received by taking the power of 2. So 2 to the power of 0 gives us 1, 2 to the power of 1 gives us 2, 2 to the power of 2 gives us 4, etc., etc. We can say that up to the third position, if we only look to the right at the 2 first bits, we have up to 2 by 2 possible combinations of these 2 bytes. These 2 can either be both turned off, can either be turned on, and either one can be turned on while the other is off. We therefore have 4 possible combinations, and that's why the third bit is represented by the number 4. If we take the 3 bits, how many combinations do we have for 3 bits now? Well, it turns out we have 8 possible combinations. Take a sheet of paper and try it out. So these are the rules that define our pattern for representing numbers within a byte. So if we follow this rule, the number 3 is now represented by turning on bit number 1 and bit number 2. Bit number 1 represents the number 1. Bit number 2 represents the number 2. We added those 2 together and we get a 3. The number 4 will be represented by just turning on the third bit, because number 4 is representing the third bit. Using the same logic, how do we represent the number 26? We turn on the bit that is represented by 16, then we turn on the bit that is represented by the number 8. 16 plus 8, that gives us 24. So we're missing 2. We have the second bit that is represented by the number 2 to add on to that. So these three specific bits come together to represent the number 26. Now, if we turn all 8 bits, what do we get? We need to add 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128. That brings us to 255. So the largest possible number, whole number, that we can represent using a single byte is 255. So how do we represent larger numbers? How do we represent 256? How do we represent 2008? Well, we do that by concatenating 2 bytes together. In this way, we have extended the 8 bits available within 1 byte into 16 bits that now allows us a combination of 16 possible ones and zeros along those 2 bytes, whereas the 16th bit represents the 65,536. So you can imagine that many combinations are possible with 16 bits. However, we must consider representing also negative numbers. For that, we sacrifice the most significant bit, which is the leftmost bit here, to represent the negative sign in case we are representing signed numbers as opposed to unsigned numbers. So with unsigned numbers, we use all of the bits available to represent positive numbers only. With signed numbers, we represent both negative and positive numbers by using the leftmost or most significant bit along with 2 complements of the rest of the bits. Let me show you what I mean. This is the regular representation of 266. We're taking 256, we're adding 8, and we're adding 2. That brings us to 266. Now, in order to do the trick to represent the negative 266, we first take the 266 representation and apply the first complement to it, which is basically just toggling all of its bits. So every bit that was 0 now becomes 1, and every bit that was 1 now becomes 0. This is 266 first complement. Then we do the second complement on that representation, which is basically adding 1 to the ones complement. Adding 1 in binary means that we are running from the right, from the least significant digit, from the right to the left, the direction, on a representation. And whenever we encounter the first 0, we stop, and then we flip, we toggle all of the bits that we encountered so far. So in our example, we start with the first bit, which is 1. Since it's not 0, we are continuing to the next bit from right to left, which is 0. So now we've encountered our first 0. So what we do now is that we flip that 0 to 1 and the previous 1 to 0. So as you can see, these 2 bits were flipped back to what they were originally by just adding 1 to the ones complement. And our leftmost bit is turned on, which tells us that this represents a negative number. So this way we tell our computer that this is a negative number in case we have defined for the compiler that this is a signed number. So this bit is used to represent the negative number if it is 1, and that it must be decomplemented back to this representation of 266 together with the minus sign that is represented by this bit. So this is how we would represent minus 266. So we know how we can represent numbers. How about characters, strings? What we can do is decide that each character is represented by a numeric code. Now, since we already know how to represent and store numbers, we can store strings by storing many, many numbers one after the other. For that, we have an ASCII table, ASCII. That is the very first table that was defined in the first days of computers to represent the alphabetical set of strings, of characters. Now, an ASCII table has only 1 byte to represent characters. And we know that 1 byte is very limiting. We can store up to 255 numbers or 128 characters if we omit the leftmost bit. But the ASCII table is still very popular, and it represents all of the characters in the English alphabet and some other characters as well. For example, the letter A in capital is represented by the number 65. The letter B, capital, is represented by the number 66. The space character is represented by 32. The double quote is represented by 34. The number 3 as a string, as a character, not as a number, is represented by code 51. But how do we represent all other languages? For that, the Unicode method was developed. The Unicode table can be very, very long. There's no longer a limit of the number of bytes to represent characters. You can decide how many characters you want to add together to represent whatever character you need. So the Unicode table actually can hold tens of thousands of characters, 120,000 characters. All of the world languages and other symbols are included and represented by the Unicode method.
In this video, we're going to focus on operations associated with binary numbers. How do you add two binary numbers together? How do you subtract them? How do you multiply them? How do you divide two binary numbers? So let's start with the basics. What's 0 plus 0? 0 plus 0 is 0. Now what about 1 plus 0? How can we add those two binary numbers? 1 plus 0 is 1. Now there's some other basic rules to go over. What about 1 plus 1? In this case, we need to carry over. 1 plus 1 is going to be 0, but you need to carry over a 1. And so you get 1, 0. So basically, 1, 0 has the decimal equivalent of 2. Now what if you have 3 ones? How can you add this? In this case, it's going to be 1, and you carry over a 1. Let's write that here. And so you get 1, 1. So if you have 3 ones in a single column, it's going to produce an output of 1, 1. Now let's work on some example problems. Go ahead and add these two binary numbers. 1010 plus 1001. Now the first thing you should do is you should line up these numbers. And then add up the numbers column by column. So here we have 0 plus 1, which is 1. In the next column we have 1 plus 0, which is also 1. And then for the third column, 0 plus 1, that's 0 plus 0 rather, which is 0. And then for the last one, it's 1 plus 1, which is going to be, based on the last two examples, 0, but you need to carry over a 1, so you get 1, 0. Now, to check the work, let's convert each binary number into a decimal number. So let's separate this into columns. So this is 1, 2, 4, 8, and 16. So 1010 is going to have the decimal equivalent of, this is going to be 8 plus 2 because it's in this column. 8 plus 2 is 10. So that's the decimal equivalent of 1010. Here we have an 8 and a 1. So 8 plus 1 is 9. 10 plus 9 is 19. So here we have a 16 plus a 2 plus a 1. So that adds up to 19. And so we can see that we have the right answer. So this is our answer right here. So that's how you can add two binary numbers. Now let's go ahead and try another example. Go ahead and add these two binary numbers. Feel free to pause the video if you want to try this example. So let's start with the column on the right side. 0 plus 1 is going to be 1. And then in the next column we have 1 plus 0, which is 1. And then it's 1 plus 1, which is going to be a 0, but we need to carry over a 1. Now for the fourth column, it's 1 plus 0 plus 0, which will equal 1. And then we have 0 plus 1, which is 1. And then next is 1 plus 1, which is 0, but carry over a 1 to the next column, which will give us 1. So now let's confirm our answer. But let's separate everything into columns, just like we did before. So this is going to be 1, 2, 4, 8, 16, 32, and 64. So let's get the decimal equivalent of the first number. So we have a 32 plus a 4 plus a 2. 32 plus 4 is 36 plus 2, that's 38. And then for the next one, we have a 32 plus 16, which is 48. 48 plus 4 is 52, plus 1, that's going to be 53. Now 8 plus 3 is 11, carry over the 1. 5 plus 3 is 8, plus 1, that's 9. So this should equal 91. So we have a 64 plus 16, so that's 80, plus 8, that's 88, plus 2 is 90, plus 1, 91. So we can see that we do indeed get the right answer. And so now you know how to add binary numbers. As you can see, it's not very difficult as long as you follow the process. So make sure you remember these two things. When adding 1 plus 1, you're going to get a 0, but you need to carry over a 1 to the next column. And so the end result is that you get 1, 0. And if you're adding 3 ones together, it's going to be 1, but you carry over another 1. And so instead of getting 1, 0, you get 1, 1. And if you remember these two things, you can easily add two binary numbers together. For the sake of practice, let's work on another example. So go ahead and add these numbers. So feel free to take a minute, pause the video, and work on this example problem. So let's start from the first column on the right side and work our way towards the left. 1 plus 1, we know that it's going to give us 0, but we need to carry over a 1 to the next column. 1 plus 0 is going to be 1. And then in the third column, we have 1 plus 1, which is 0, but we got to carry over a 1. Now for the fourth column, we have 3 ones. Do you remember what we need to do if we encounter this situation? If you have 3 ones in a single column, it's going to give you a 1 for that column, but you need to carry over another 1 to the next column. And so 1 plus 0 plus 1, we could ignore the 0, and so it's the same as 1 plus 1, which will give us a 0 for that column, but we got to carry over a 1. And for the last column, we have 3 ones again, so it's going to produce a 1 for that column, but we need to carry over another 1 for the next column. So 1 plus nothing is going to give us 1. And so this here is our final answer. But as always, let's confirm it. So let's begin by drawing lines to separate the columns from each other. And then let's write the powers of 2. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 to the third power is 8, 2 to the fourth power is 16, 2 to the fifth is 32, and 2 to the sixth is 64. So let's convert the first binary number into its decimal equivalent. So we have a 32 plus 8. 32 plus 8 is 40, plus 4, that's 44, plus 1, so that's a total of 45. Next, we have a 1 for the 32 columns, that's 32, plus a 1 for the 16 column, so 32 plus 16, that's 48, plus 8, that's 56, plus 4, that's 60, plus 1, and so that's going to be 61. Now 1 plus 5 is 6, 4 plus 6 is 10, so we get 106. Now we have a 64 plus a 32, so that's 96. 96 plus 8 is 104. 104 plus 2 is 106. And so our answer is indeed correct. So this is the final answer right here. 1101010. Now let's move on to our next topic, that is how to subtract binary numbers. So let's start with this. What is 1 minus 0? 1 minus 0 is simply 1. Now what about 1 minus 1? 1 minus 1, they cancel, and that's 0. Now what if you have 1, 0, but you wish to subtract it by 1? What will you do? Now 1, 0 as a binary number is equivalent to 2 in the decimal system. And 1 is just 1 in the decimal system. So 2 minus 1 should give us an answer of 1. Now, we can't do 0 minus 1 because that's going to give us a negative number. So we need to borrow. So we're going to borrow this 1. That's going to turn into a 0. And then this 0 becomes a 2. 2 minus 1 is 1. And 0 minus nothing is 0. So 0, 1 corresponds to 1. Now, what if we have this situation? Let's say it's 1, 0, 0 minus 1, 0. Now, this column is for the 1s, 2, and 4. So 1, 0, 0 is basically 4, and 1, 0 is 2. 4 minus 2 is 2. So this is the answer we should get. Starting with the first column, 0 minus 0 is 0. Now, 0 minus 1, we can't do that, so we need to borrow a 1. So that's going to disappear. That's going to change to 0, and this becomes a 2. 2 minus 1 is 1. And you could bring the 0 down if you want to. 0, 1, 0 has the decimal equivalent of 2, so this answer is correct. Now let's try this one. 1, 0, 0 minus 1. Go ahead and subtract those two binary numbers. So we can't do the first column. 0 minus 1 will give us a negative number, so we need to borrow a 1. Now we can't borrow anything from this column because it's a 0. So we need to borrow a 1 from a column that has a 1. So this becomes a 0, and this column becomes a 2. So anytime you cross out a 0, replace it with a 2. It's going to work if you do it that way. Now we still need something in this column. So let's borrow a 1 from the 2. So this becomes a 1, and this becomes a 2. Now we can subtract. So 2 minus 1 will give you 1. And then you can bring down the 1 here because there's nothing to subtract it. 1 minus 0 will be 1. And you can bring down the 0 as well. Now let's check the work. So 100 as a binary number has a decimal equivalent of 4. And here we just have 1. So 4 minus 1 is 3. Now looking at this number, this is 1, 2, 4. So we have a 1 with the 2 and 1. 2 plus 1 is 3. And so that tells us that we do have the right answer.